All right, one more problem involving static friction. We have a car parked in a hill. The hill is inclined at 32 degrees from the horizontal. We want to find the force of friction. Oops. What is the force of friction? Sorry, typo, on the car. The coefficient of static friction, so this is telling us that mu sub s is 0.85. Mu sub k is 0.64. So finding the force of friction. Free body diagram. We know there's a force of gravity pointing straight down to the center of the earth. There is a normal force perpendicular to the surface. If there was no friction, if this was a perfectly icy hill, the car would accelerate down the hill. Well, this problem tells us the car is parked, so the force of static friction needs to point up the hill in order to keep the car from sliding down the hill. So this is our free body diagram. With this being on an incline, I like to rotate my coordinate system. That simplifies how many vectors have both x and y components. If there was acceleration, it simplifies that as well. But in this case, our car is parked on the hill. Let me draw that. mg over here so that I can draw in the y component and x component of mg. The incline angle is always the angle between the force of gravity and the new y-axis. So this y component will be mg cosine 32. This x component will be mg sine 32. So we know the car is parked. We know the acceleration in both the x and y directions will be 0 in order for the car to stay there. So in the x direction, we have static friction pointing up the incline. We have mg sine 32 pointing down the incline. They need to balance each other out in order for that acceleration to be 0. In the y direction, we have the normal force in the positive y direction, and then the component of gravity, mg cosine 32. Now, we know that we can say that the force of static friction is mu times n. But remember, this is the maximum possible value. It's not necessarily the actual value in the problem. Let's go ahead and calculate this. So mu 0.85, the mass of the car 1500, g 9.8, and then cosine of 32. So I've essentially just plugged in mg cosine 32 for the normal force, because I know that's what it needs to equal to balance out the forces in the y direction. $10,596. Now, I'm not worrying about rounding right now. That's not my answer per se. This is the biggest the force of static friction can be. It doesn't mean it is that value. But I do want to know how big it can be to make sure that the car is not sliding down the incline. So coming back to the forces in the x direction, when we say the static friction force needs to equal mg sine 32, this gives us the force of static friction needed to keep the car parked. So let's calculate this. So mg sine 32 I'm getting 7789.8. So this is essentially telling me that the force of static friction needs to be to 2 sig figs, 7,800 newtons, in order for the car to be parked on this hill. This value is smaller than the value calculated using mu s, that coefficient of static friction, times the normal force. That means the car is parked. This friction force is not bigger than the maximum possible value. That also means this 7,800 newtons is the force of static friction on the car. The force of static friction can be any value up to this maximum value. In this case, the friction needs to be 7,800 newtons to counteract this 7,800 newtons down the incline due to gravity. That's what's keeping the car parked on the incline. So static friction, we have to consider whether or not the object will stay stationary. If it does, we need to figure out the value needed to keep it stationary and compare that to the maximum value.